welcome to The Explainer. Today, we are diving into an absolute superpower in programming. We're talking about giving your programs a permanent memory. Think about every single app you use on a daily basis. Your web browser saving your login, a video game remembering your high score. Literally none of that would be possible without the core concepts we are going to unpack today. We are taking you from temporary, fleeting operations to completely mastering persistent storage. Let's get right into it. So what if your Java or C program could save data even after it closes? Okay, normally when you run a program, right, its variables and data, they just live temporarily in RAM. The exact moment that program ends, it suffers from total amnesia. I mean, it's worse than a digital goldfish. Everything is just wiped completely clean. But that is exactly where file handling becomes incredibly powerful. It interrupts that amnesia. It gives your software the ability to leave a lasting footprint. There's this fantastic quote from our source material that says, "File I/O is what gives your programs a memory." And honestly, that just beautifully captures what we're doing here. You know, we aren't just typing out lines of code. We are essentially teaching our applications how to remember. We're giving them the ability to save data, take a breather, and then pick up exactly where they left off the very next time you launch them. So what are we actually going to achieve today? Well, by the end of this explainer, you're going to know exactly how to build mini applications that permanently store and read data. And we'll look at this across languages like Python, C, C++, and Java. And honestly, the best part is that the core logic we're learning applies universally. You're going to walk away with a practical, hands-on skills to ensure your program can now remember information permanently. Before we start writing anything, we need to understand the two main flavors of files we're dealing with. On the left side, we have text files. These are all about simplicity. They use ASCII or Unicode, which basically means you can just open them up in Notepad and read what's there like a normal human. They're perfect for basic notes or configuration settings. But then on the right, we have binary files. Now these are kind of like the secret agents of the file world. They hold data in this completely non-readable raw memory format. They are incredibly efficient, mostly used for storing complex stuff like images or compiled structures directly as a stream of bytes. Now, whether you're using text or binary, Python, Java, or C++, it really doesn't matter because there is a universal workflow you have to follow. It's a super simple three-step process. Step 1, you open the stream to establish a connection. Step 2, you process the file, so reading from it or writing to it. And step 3, which is absolutely crucial, folks, you close the stream. You have to close it to terminate that connection and free up your system resources. That logic, rock solid across every programming language. Okay, let's dive into this whiteboard mindset for a second. Try to visualize this. Data is flowing out of your active program, it's traveling through that data stream we just opened, and it's landing safely inside a file right on your hard drive. Program to file to save data. And when you actually build this, you can visually demonstrate that your data remains saved even after the program completely closes. The file just sits there on the disk, patiently holding your information until the exact moment you need it again. And that visual brings us right into the full practical workflow of a real application. First, we write the data. Then we make sure it's actually saved to the disk. Later on, our program can go back, read that same stored data, and display it back to the user. Write, save, read, display. It's a complete closed cycle of data persistence. This means your program actively remembers and outputs information it stored days or even weeks ago. Let's actually ground these high-level concepts in reality for a second and look at some C programming documentation. Once you've opened a file using a file pointer, you rely on a few specific functions to handle all the heavy lifting. Checking out these prototypes gives you a really good glimpse into how the system expects you to package and define the data that you're moving in and out of those files. Now, what's really interesting here is the specific syntax for fread and fwrite in C. If you look closely at the parameters, both of these functions require a pointer to a memory buffer. They need the size of each item in bytes, the number of items, and the file pointer itself. Fread grabs a stream of bytes from the file and pulls it into your buffer. Fwrite does the exact opposite. It pushes your buffer out to the file. They manage these raw streams of bytes with just incredible efficiency. All right, so we've got this amazing superpower to write files permanently. But what happens when this superpower hits real-world obstacles? I mean, what if you try to save a file, but your program lacks the necessary user permissions? Or even worse, what if the user's hard drive is literally full? In the real world, file operations definitely do not always go according to plan. Let's quickly run through what we call the common file villains. Trying to read a file not found? That's gonna crash your program. Lacking admin rights? You'll get slapped with a permission denied. Disk full will stop your writes dead in their tracks.
Accidentally overwriting because a file already exists? Say goodbye to your data. And trying to read past the end of file is just going to cause wild, unpredictable behavior. If you fail to check for these errors, your program is going to terminate prematurely, guaranteed.
To fight off those villains, we have to build safety nets. In C, whenever you attempt to open a file, you absolutely must check if the returned file pointer is null. If it is, boom, the open failed. From there, you can use functions like para-error to print the exact system error, like no such file or directory. When you're writing data, fwrite acts as a safety net to detect if the disk is full. And if you're using Java, you'd wrap your file operations in a try-catch block to just gracefully intercept any of these issues. Handling errors gracefully? That is exactly what separates a fragile script from robust, professional software. So, here is a really crucial point. How do we manage existing data? If you open an already existing file in basic write mode, you are going to instantly overwrite and erase every single thing inside of it. That's a nightmare. That's where append mode comes to the rescue. In Python or C, you use the letter A, and in C++, it's ios/app. Append mode specifically opens a file to add new contents to the very end, keeping all your previous data perfectly intact. This is what allows your programs to maintain ongoing logs rather than wiping their memory fresh every single time they start. Okay, let's see this in action with our first mini project. Using Python, we can actually build a time-stamped journal and an interactive to-do list in just a couple of minutes. By opening a file like journal.txt in append mode, every single time the user runs the program and types a note, it stamps the time and drops that note at the very bottom of the file. A to-do list manager works the exact same way. You read the tasks using read mode and add new tasks using append mode. It's a fully interactive application powered entirely by persistent memory. For a slightly more advanced architecture, we can look at a C-based employee record system. Now, this project uses structured data, specifically an employee's name, age, salary, and ID number. By setting up switch cases for a menu, the user can easily add, delete, modify, or view these records. And because it uses C file handling functions to write this struct data to a binary file, the company keeps track of all employee records permanently on their disk. And hey, you could easily apply these exact same concepts in Java using a file writer to create a permanent notes application that saves exactly what a user types. Let's take a step back for a second. Why does mastering this matter so much to you as a developer? Because file handling is literally used in almost every real-world application. It is the absolute foundation of persistent storage. Whether you're saving user profile data, writing application error logs, generating massive corporate data reports, or even just saving a simple configuration file, the underlying mechanics are exactly what we've covered today. It makes your code immediately useful in the real world. All right, I want to leave you with a quick micro-challenge to really test this new advanced systems mindset. Imagine you've built a basic note-taking app, but right now it overwrites its data every single time it saves. How would you modify your code so users can append multiple notes instead of replacing the old data? Think back to the file modes we just discussed. Once you solve that, you've truly proven that your program can now remember information permanently. Thanks so much for joining me on this explainer, and keep building.